Good morning. It's O Dark 30 here. It's a good time to make another video. I've just kind of looked through sections 3.1 and 3.2, and I'm thinking maybe your head is spinning right now. You know, probability has a way of just climbing all over your back. I mean, if you think about it, we've just read section 3.1. That's just some definitions. They didn't seem particularly difficult to understand, and yet here we are in section 3.2. And I've got to believe a lot of these questions are really, they really sound like alien technology to you. So I wanted to help clean that up a little bit. You have to just keep working on it. It gets a little easier to understand as you go along. You know, it's strange. I haven't seen a probability text before that is treating this subject in this manner. Generally, what you do is learn the material that's in section 3.3, which is called the addition law and the multiplication law. They're the two primary laws that you're going to use to calculate different types of probabilities for what you call compound events. And when you do that, the idea of independence and mutual exclusivity just comes in as a subset instead of getting its own little section as the authors of the OpenStax text had chose to do. I can't explain why that is. I don't necessarily think it's a bad thing, but nonetheless, you know, we've got to play the hand that we're dealt here. So, these 20 view graphs, which I'm going to click through pretty quick as soon as we get going, are a problem which are getting you to address the question, are these two events mutually exclusive, are these two events independent? And I've got to tell you, the two ideas, though you probably never ran into either of them, at least in this, in the manner in which they're used here before, they're not terribly difficult to understand. Independent means just that. Two or more events are independent if they just can't influence each other at all. And the example that is normally given is, here's a deck of 52 cards. If I pull out a single card, Ace of Hearts, what was the probability of that happening? Well, there's only one Ace of Hearts in this deck. Trust me, only one Ace of Hearts in this deck. Yet there's 52 cards. So the probability of yoinking out the Ace of Hearts is 1 chance out of 52. Now watch me put the Ace of Hearts back, okay? Watch me put it back, and let's ask, well, what's the probability now, having replaced it, that I pull out the Ace of Hearts again? And you go, oh my God, some sort of sleight of hand. I know it seems very unlikely, and it would have been if I didn't know exactly where it was, but the fact is, that second draw, the probability of getting the Ace of Hearts was again 1 out of 52. Why wouldn't it have been? In the first case, the deck had 52 cards in it and 1 Ace of Hearts. In the second case, same exact thing. In those two cases, those two events of drawing on a deck of cards with replacement makes the two draws independent of one another. As opposed to, if I was to pull out a card, 4 of Hearts, and throw it on the table, and now draw a second card out of here, you might ask, what's the probability of pulling a 4 of Hearts out of this deck? Well, I got to tell you, that 4 of Hearts is sitting over on my desk right now. There is no 4 of Hearts in this. So suddenly, something about taking that card out and not replacing it has changed this deck. And in fact, the probability of pulling out an Ace of Hearts out of this deck is not 1 out of 52. There's not 52 cards here anymore. There's 51 cards. So the chances of pulling out that Ace of Hearts is 1 out of 51. So somehow that fact that we didn't replace it, we drew a card and didn't replace it, changed everything. Those two events, drawing cards without replacement, are dependent. What you do on the first event influences what happens on the second. That's dependent and independent. Mutual exclusivity is, and oh, by the way, that dependent and independent, that typically applies to situations in which the two events are in some sense sequential, right? And that's not true of mutual exclusivity. For mutual exclusivity, the issue is whether or not two events can happen on the same trial of the experiment. Experiments have multiple outcomes that occur on a given trial. Yeah, flip a coin. One of two things can happen. Roll a die. One of 6 things can happen. Multiple outcomes. The question with exclusivity is, can 2 of those outcomes occur at the same time? So think back to the previous adjunct video in this section. 100 people, 52 males, 48 females, 87, if I believe, right-handed people, 13 left-handed people. And the question that came up was, what's the probability of pulling out a left-handed female? Reaching into those 100 people, pulling one out, you're a female and you're left-handed. What's the probability? All we did was we counted up how many females, we counted up how many left-handed people, 48 females, 13 left-handed people, and then we said, we were careful to say, oh wait, we counted those 4 left-handed females as both left-handed and females. We counted that improperly twice. Let's pull that out of the sum, right? And the reason we did that is because the act of being female, the act of being left-handed, were not mutually exclusive. It was possible to pull out a left-handed female, not mutually exclusive. Those can happen at the same time. Okay? Think for just a moment about pulling coin. In contrast to that, think of pulling coins, pennies, nickels, dimes, quarters out of a piggy bank. Okay? And let's calculate, in the same way we calculated the probability of identifying pulling out a left-handed female, let's find the probability of female or left-handed. Let's find the probability of pulling out on a single draw a dime or a nickel. So what do? You count up all the dimes, you count up all the nickels, just like we counted up all the females and all the left-handed people. In the case of the females, when the 2 events were not mutually exclusive, we had to go make sure that we didn't double count. In this case, since there is no dime nickel, right, those 2 events, pulling out a dime and a nickel, both on the same, can't happen. You can't pull out a dime nickel on a single draw. The event of pulling out a dime and pulling out a nickel, those 2 events are mutually exclusive. Can't happen at the same time. Let's go do this. Okay. Actually, let's do something else. Let's break right now. I tell you, keeping these videos at 6 or 7 minutes is something that just defies me. The best I can do is just sort of break them up. So let's just take a beat. You guys can catch your breath, so can I, and we'll come back and work on this view graph package. All right? So here's an even more complicated situation. Let me read it to you here. It says 70% of the fans are rooting for the home team. I think this is a basketball game. 25% of the fans are wearing blue. 20% of the fans are wearing blue and are rooting for the away team. Got to read it carefully. Of the fans rooting for the away team, 67% are wearing blue. First thing that we ought to do is let's get that English out of the way and get some probability terminology down so that we can start to work with some of these probability laws. So the statement, 70% of the fans are rooting for the home team. Let's call the fans rooting for the home team H. The way you would rewrite this is the probability of H is 70%, meaning if you got 1,000 people in an arena, you go look at row 27, seat A, and without knowing anything about the poor guy sitting there, you know that there's a 70% chance that he's rooting for the home team. Okay? That's what that means. And likewise, that poor guy, you know that there's a 25% chance that he's wearing blue. You would write the probability of wearing blue is equal to 25%. All right? The next one down, the third bullet here that we're working on, 20% of the fans are wearing blue and are rooting for the home team. You're going to find that you have to read these things very carefully. You see that little and, little 3-letter word? Of the fans are wearing blue and are, that means that what that English says is that the probability of wearing blue, B, and the probability of rooting for the away team, A, the probability of A and B is 20%. And there you have it. And the last bullet is particularly tricky. it says of the fans rooting for the away team, 67% are wearing blue. Now, I tried to get you to look for the word given. I warned you that there's other ways to make conditional probability statements without using given. And here's one of them. It says, of the fans rooting for the away team, given that we're only thinking about fans rooting for the away team, right? Right? That, as we said, that word given, conditional probability, it reduces the sample space. We're not going to look at everybody in the arena. We're just going to look at the fans rooting on the away team. Of those fans, 67% are wearing blue. So you would write that as the probability of wearing blue given that you're rooting for the A team. A, probability of B/A is 67%. All right, so there's the translation. What's the next thing you do? The next thing you have to sort of do in this problem is to recognize that if you're not rooting for the home team, you better be rooting for the away team, or you should leave the stadium. In other words, the complement of H, rooting for the home team, is rooting for the away team. And that's important because if those two are complements, then the probability of rooting for the away team plus the probability of rooting for the home team is 1. Right? And we know that the probability of rooting for the home team, look, it's looking at us in the face there, 70%. It means the probability of A is 30%. Okay, we're kind of ready to rock and roll here, but let's take a break before we begin to discuss the independence and the mutual exclusivity. All right, so we're back, and we're ready to answer the question, are A and B independent? And so how do we do that? Well, we apply the definition, and maybe you're asking what's the definition, and here it is. If two events A and B are independent, we've talked about this before, then the probability of A and B is just the product of their two individual probabilities. We'll talk about where that came from in just a moment, but since I now know P of A, P of B, P of A, and B, let's just go check. P of A is equal to 30%, P of B is equal to 25%. Multiply those two together, you should get 7.5%. But look, P of A and B is 20%, not 7.5%. So that equality doesn't hold. It doesn't hold because A and B are not independent events. They're dependent events. You know, it's as simple as that. Now, before that begins to sound like magic, remember where that relationship came from. It came from the conditional probability statement, which says that the probability of B given A is the probability of A and B divided by the probability of A. And you kind of know that in a counting sense, again, from that example, male, female, left, right-handed case that we did, because if you wanted to find the probability of being left-handed, given that you're female, remember that given that you're female restricts the sample space, not all 100 people, just the females. You count among just the females how many are left-handed. The answer was 4. You divide that by how many females there were. There were 48. That probability of being left-handed given that you're female was 4 over 48. Okay. Now, if you divide top and bottom of that fraction by the total number of people, you don't get the number of left-handed females, but the probability of being a left-handed female. And down at the bottom, you don't get the number of females, you get the probability of being female. That's what that relationship right there says, that the probability of B given A is the probability of A and B divided by the probability of A. Okay, then if you look down to that last sentence, if A and B are independent, then the probability of B given A is just the probability of B. They're independent. B doesn't depend on A. So when you substitute that back into the above, you get that relationship for independence. P of A and B is equal to P of A times P of B. Yep. So let's take the next step. And let's ask, are A and B mutually exclusive? Okay, different question, right? Let's apply the definition. What definition? If A and B are mutually exclusive, they cannot occur at the same time. So P of A and B must be equal to 0. But just look right above, P of A and B is 20%. And so there you have it. A and B are not mutually exclusive. So see, it becomes fairly easy to determine these things if you know all the parameters that are in these two definitions. And to some extent, you don't need to know the definitions at all. You just need to kind of understand the context and understand if two things can happen or not, and if two things depend on one another or not. Okay? Very good. Thanks.